We will continue where we left off. Open example in the chapter. The dean of a school of business claims that the average salary of the school's graduates 1 year after graduation is $800 per week, with a standard deviation of $1,100. The second year student would like to check whether the claim about the mean is correct. He does a survey of 25 people who graduated 1 year ago and determines their weekly salary. He discovers the sample mean to be $750. To interpret his finding, he needs to calculate the probability that a sample of 25 graduates would have a mean of $750 or less when the population mean is 800 and the standard deviation is $100. We want to compute the probability that x bar is less than 750. Right? Although x is likely skewed, it is likely that x bar is normally distributed. The mean of x bar is mu of x bar is equal to mu, population mean is equal to 800. The standard deviation is given by sigma of x bar is equal to sigma over the square root of n. N is 25, 100 divided by 25, 5 into 100 goes 20 times, so that is 20. Sigma of x bar is 20. So you've got the probability x bar is less than 750 is probability x bar minus mu of x bar over z of x bar as probability of z is less than 750 x bar minus the mean. Population mean is 800 over 20. My cursor, here it is. That is, the probability z is less than minus 2.5 is equal to minus 0.5 minus probability z lies between 2.5 and 5. That is calculating probabilities in the usual way we've done using the table. So it's 0.5 minus 0.4938, which gives 0.0062. The probability of observing a sample mean as low as 750 when the population is 800 is extremely small. Because the event is quite unlikely, we would conclude that the dean's claim is not justified. Bravo. Standardizing the sample mean. This is standardizing the sample mean is shown here. The sampling distribution can be used to make inferences about population parameters. In order to do so, the sample mean can be standardized to the standard normal distribution using the formulation z equals x bar minus mu over sigma over root n. And this is just an extension of what we've seen. We already know about probabilities. Probability z lies with minus 1.61 per 6 is 0.95. For the sampling distribution, probability z is equal to x bar minus mu over sigma over root n. And replacing that, probability that x bar minus mu over sigma over root n is equal to minus 1.96 less than 1.96 is also equal to 0.95. Don't need to focus much on this mathematical aspect of the course. That's with a little algebra we can play around and end up with this. In general, the probability that x bar lies between mu minus z alpha over 2 times sigma over root n and mu plus z alpha over 2 times sigma over root n. This is equal to 1 minus alpha, where alpha is, as you learn, is called the significance level. All probability statements about x bar, which we will use in statistical inference. And there are various aspects which are shown here. There's another way of checking the dean's claim. You don't need to focus much on that. We just go through that briefly. The probability that x falls between 76.8 and 8.9 is 0.95. It is unlikely that we would observe a sampling mean as low as that when the population is 800. This is another way of looking at it. This is excluded, sampling distribution of the proportion. This is excluded from a course at the moment. It's included in the course outline, but it's excluded in our course. Normal approximation to the binomial. This is included in the course outline. It's not applied in this course at the moment, and so forth. This becomes very useful. Sampling distribution of the proportion. Against this is excluded from the course. Sampling distribution of two means also excluded from the course. And that is the end of chapter 9.